All right, so let's identify the hypothesis and conclusion of the following statements. If we have a pep rally, then our classes are shorter. We have said that hypothesis is going to come immediately following the word if. So if we have a pep rally, is our hypothesis. And our conclusion is the statement coming immediately after the word then. Then our classes are shorter. Therefore, our classes are shorter is my conclusion. My next statement says, a number is divisible by 10. So this one didn't start with if. A number is divisible by 10 if, oh, there it is, if its last digit is 0. So this conditional statement is not in the same order as the two we have done before. Our hypothesis and our conclusion are in different places, and that's okay. We still follow the rule that our hypothesis immediately follows the if. So if its last digit is a 0, is our hypothesis. And then we have to look at the rest of the statement. What is left? The word then is not included, but if we take into account what is left, a number is divisible by 10. This is our conclusion. If we read this differently or backwards, we could say, if its last digit is 0, a number is divisible by 10. So it's just missing the then, which sometimes happens, but it's always going to be the part that isn't the hypothesis. All right, the truth value is going to tell us whether a statement is true or false. And this is much more based off of what we know about the information provided. So if you have $5, then you have 5 $1 bills. Well, what if you have a $5 bill? Would that make this statement false? It would. What if you had 20 quarters? That would also be $5. So we have to say the statement is false because we can think up of a reason why you could have $5, but it not be made up of 5 $1 bills. Next, we have, if I roll 2 6-sided dice and the sum of the numbers is 11, then one die must be a 5. So think about dice, 1 through 6. What combination of numbers, of two numbers from those two dice, could add up to equal 11? The largest number available is a 6. The smallest number available is a 1. 11 is a pretty large number, so we have to think about, okay, 6. If we had 6 on one dice, what would the other dice have to have? It would have to have a 5. So that would be 11. Let's move on to 5 for our first dice. If our first dice has a 5, then the second dice has to have an 11. If we go smaller than that, 4 plus what equals 11? Well, that would be 7, but there is no 7 on a 6-sided dice. So the only thing we could have is a 6 and a 5 or a 5 and a 6. So one of those die has to have a 5 on it. So that is true. So our counterexample is a false example, or an example that is false, that we use to show a conjecture, so what we've been talking about, or statement is not true. So if I can think of a reason or an instance or just one example that says this statement or this conjecture doesn't hold true for all circumstances, then it is not true. So looking at our example here, which of the following is a counterexample of the statement? If a number is an integer, then it is a positive number. So integers, if you don't remember, integers are whole numbers that range from negative infinity to infinity. So they cover negative numbers and positive numbers, but they don't include decimals. So if we look at our examples, we have 4.24. This is not an integer. It has decimals. We do not include that. And then we look at 3. Is 3 an integer? Yes, it is. Is it positive? Yes. So it is not a good example of a counter example. C says negative 1.5. This is also not an integer because it has a decimal. And then we look at D. D is a negative 7. Negative 7 is an integer. And it is negative. So it is our counter example. Now that might not make as much sense if you weren't super familiar with integers and the rules surrounding them. So let's look at something a little more real world. If you were competing in the Winter Olympics, so remember Winter Olympics, things that are cold, things that happen on ice or on snow. There's not a lot of other things that happen with the Winter Olympics around that. So it's usually involving ice or snow. Then you compete on snow. Well, let's see if that's always true. First, let's eliminate what isn't in the Winter Olympics. Swimming. Swimming is a summer Olympic sport, so swimming is not going to be a part of this. And football. Football is not in the Olympics at all. Not American football. Like soccer football is in the Olympics, but American football is not. So we can cross that out. So we are left with snowboarding and speed skating. We are trying to come up with a counterexample that states that the Winter Olympics don't always have to happen on snow. So snowboarding does happen on snow. That would not be a good counterexample for us. That would tell us it is happening on snow. So speed skating happens on ice inside of a rink. So it has nothing to do with snow. So speed skating is in fact our counterexample.